Good morning, my name is Alexandra Kokkinaki and I work in the National Oceanography Centre in the UK. Today I will take you through the journey towards fairness that we took with my colleagues of the Marine Subdomain during the EnVriFair project. This journey was funded by the EU EnVriFair project, whose overarching goal was to connect the ESFRI cluster of environmental research infrastructures EnVri to the European Open Science Cloud EOSC. In this presentation, I will focus on the fairness journey of the marine domain, including challenges and solutions to those challenges. I will now introduce you to the marine landscape, which consists of 5 RIs that represent different scopes. EuroArgo measures water properties using Argo and BioArgo floats. ENSO focuses on data measured by moorings and fixed observatories. ICOS Marine deals with carbon, while SeaDataNet and LiveWatch are data infrastructures for the marine and biodiversity domains, respectively. The main objectives of the EnVriFair project were to enhance the fairness of the 5 marine RIs, taking into account the priorities of the different RI users, to implement fairness enhancements within each RI at 3 different levels, to better serve their users, to facilitate marine domain integration, and to contribute to the EnVri cluster service development. And finally, to showcase the above-mentioned achievements, focusing on a set of essential ocean variables, EOVs. To achieve the above, we applied the following steps. The first step was to assess the RIs in terms of fairness and to report on their strengths and weaknesses. Based on the assessment, each RI identified developmental priorities to mitigate their weaknesses by means of a roadmap. Next, each RI developed an implementation plan based on their priorities. And finally, we all worked together on defining how to demonstrate our achievements using EOVs. In order to assess the fair maturity of RIs, it was important to collect current information about RI services and their data. The first challenge we faced was that at the time of the assessment in 2019, not many tools were available. We agreed to work closely with the GoFair initiative and be guided through the fairness assessment. GoFair provided us with questionnaires that had to be completed by each RI. As the FAIR concept and terminology are quite complex, to effectively complete the questionnaires, the RIs had to be trained on the FAIR principles, so education and training sessions were held. We also agreed to communicate regularly, initially in person, but due to COVID we started having regular virtual meetings. The plan was that after the completion of the questionnaires, we would collect the answers, analyze strengths and weaknesses of each RI, and propose a priority list of possible improvements. The questionnaire was an online Google form that looked like this, and all responses from the marine RIs were collected in a Google spreadsheet. From a first analysis, it became quickly obvious that the responses to the questionnaires by RI representatives were not directly usable for downstream analysis, mostly because of insufficiently answered questions, free text answers that needed harmonization. The answers were reviewed and post-processed in consultation with the RIs to quality control and improve the responses. The diagram below shows the steps taken to transform the RI answers in structured data collected in a triple store in order to harmonize and automate the process of producing overviews and comparisons of the RI answers. The results of the assessment quickly revealed that there was some heterogeneity among the RIs. An interesting outcome was that most RIs were fair for humans, but not for machines. The main strengths were discovered in the access protocols, the machine readability of the metadata, the extended use of controlled vocabularies, and the universal use of data licenses. The main weaknesses were the lack of unique identifiers, metadata and data APIs, and insufficient provenance information. These tables show the sum of gaps and strengths across all the RIs per principle. For example, for the findability, marine RIs captured 8 strengths and 6 gaps, resulting in a balance of 2, while on the accessibility, they revealed 9 gaps and 9 strengths, resulting in a balance of 0. As time elapsed, the questionnaires used in 2019 were replaced with the more advanced FAIR implementation profiles, which were issued by the ENVRI-FAIR in a joint activity with GoFair initiative. A FAIR implementation profile is created when a community, for example CDataNet, answers questions about their technological choices related to one or more of the FAIR guiding principles. For example, for the FAIR principle F1, the question is what globally unique, persistent, resolvable identifiers do you use for metadata records? And the answer could be a DOI, a Perl, or anything else that the community uses. And this particular technology will be registered as a FAIR enabling resource if it makes the community FAIR for this particular guiding principle. And the results are then stored in a Spark endpoint. 3 FIP exercises were performed for 2019, 2020 and 2021. We used the FIP Spark endpoint to analyze marine RI's progress. Each RI improved its fairness within 3 years with an average of 11 new FAIR enabling resources. The heat maps below show common resources used between the 5 research infrastructures. Comparing 2019 to 2021 illustrates increase in the use of common resources between RIs. For example, EuroArgo and CDataNet had only 5 common resources in 2019 that were increased gradually to 10 in 2021. Some of the lessons we learned during the assessment process was that education was crucial. Educating and training the marine RIs on the FAIR principles enabled us to complete the questionnaires more accurately, especially because the questions in these questionnaires were specialized and required specialized answers. Secondly, being educated helped RIs to make informed technological choices for their implementation plans. The questionnaires and FIPs were really important for us to be able to identify what the baseline was for us, so where we started, and to be able to continuously capture our progress. The FAIR principles coverage increased through the years with the number of FAIR enabling resources increasing and with less unanswered FIP questions. There is an increasing overlap of the technologies used across the different RIs in the marine domain, and it would be really great to be able to capture the quality of these technologies and implementations, but also their longevity and sustainability, which is something that we are currently working on in ENVRI-FAIR. Implementation plan and technical specifications. The methodology we followed was that using the overview of weaknesses and strengths per RI, and supported by the project's work packages related to common standards and common implementations, a list of planned and suggested directions for solutions to those gaps was crafted. So taking into account the RI priorities and the demonstrator requirements, an implementation plan was created per RI, and with the support of the task forces of the project, that became a technical specification for the machine-to-machine services per research infrastructure. This is how the list of weaknesses on the left and planned or suggested directions for solutions for EuroArgo on the right looks like. And this is EuroArgo's implementation plan. At the end of the implementation period, these are the achievements of the marine RIs. First, the marine RIs agreed to adopt the common use of the NERC vocabulary server NVS vocabularies. Second, the Marine Arise agreed on the use of the DCAT AP standard to describe datasets and implemented them using sparkling points. They also agreed and implemented APIs for data access, for example, using the RDAP server. And finally, they agreed on focusing on data that are available with open licenses. The EOV demonstrator. The development of the EOV demonstrator was part of the project to showcase the Marine Array fairness achievements and to also test if the achievements led to actual interoperability and integration in the marine domain. And this is how the marine landscape looked like in 2021 after the development of the implementation plans took place. All array datasets are now semantically enhanced as they are annotated with NVS vocabularies. The datasets are published using the RDAP API, and a list of EOVs has been selected that is present in all of the research infrastructures. So the candidate essential ocean variables are temperature, salinity, oxygen, inorganic carbon, ocean, chlorophyll A, and the nutrients. And this is how the EOV broker works. So the user requests an EOV parameter, for example, oxygen. The broker asks NVS to translate EOV oxygen in the vocabulary terms that the underlying RIs understand. NVS returns a list of terms that the RIs understand, and the broker uses these ones to ask the RDAPs to return all datasets that fulfill these criteria. RDAP returns the files, and these are given to the end users. As an additional technology is added in the stack of technologies for the marine domain, we will be delivering the EOV demonstrator version 2. So the marine arrays have developed sparkling points exposing data and metadata, and the EOV demonstrator will incorporate the endpoints to provide more metadata to the end user than what is stored in RDAP. So the scenario is that a user makes a geospatial query for an EOV parameter, for example, temperature, and the EOV broker asks NVS to translate temperature to the terms that the underlying RIs understand. The broker then asks RDAP to queries RDAP to provide datasets that fulfill these criteria. RDAP answers with a list of URLs and file names that could be ready for download. But this is where we add another step, which is that using these URLs, the EOV broker asks the sparkling points to provide more metadata for these files to the end user, and then the end user has a list of files with their metadata at the end. I will finish with conclusions and perspectives. To achieve all of the above, the marine subdomains had to work in two levels. One, to enhance the fairness of the marine array services, and the second one, to develop cross-domain interoperability through the services it developed. And crucial for the latter was the amount of agreements the marine array managed to make to achieve interoperability. Our progress was built on progress that has been made for a decade now in the marine subdomain, maintaining close communication and being supported, trained and educated by work packages and task forces that were common in the EMRIFAIR project. We hope that our achievements will be expandable to other arrays, will allow to serve better marine VIP users such as Copernicus and IMODNET, and that these achievements will allow cross-domain service development.